So we continue talking about neutron stars. The neutron stars, if you happen to see the flashes come by, you call them pulsars. And so as it rotates, this beam will come by, flash towards Earth. If you see those flashes, whether it be visual flashes or radio flashes or whatever kind of radiation you see, then it's on a regular pattern called a pulsar. The neutron star itself can undergo a little bit of precession, same as the Earth does. And if that happens, then the flashes don't always hit Earth, and so you'll see them flashing regularly for a while. Then you start missing a few. Then you see them regularly flashing for a while, and so forth. So theorists, when they're studying this, and astronomers have to realize. So the flashes come at a regular basis, a regular period here. Most neutron stars flash in very short time period. We talked about how fast these things rotate, and so they can flash in every second. Some of them a half second, some of them at once every several seconds. There are a few rare kinds that something else is going on that flash in just a few thousandths of a second. We call those millisecond pulsars. So you get the neutron star. It's part of what you get from a supernova. And so a famous supernova remnant was the Crab Nebula. And so on the left here, this photograph shows a time exposure of the Crab Nebula. And when you look at the Crab Nebula, you see the big cloud of expanding gas. And so what you would do is, in order to study that, you normally take a really long exposure photograph because the gas is very dim. But with the idea that this might be a supernova remnant and the neutron stars might actually exist, then Bada helped lead the way of doing very short time exposures, in which you don't see much of the nebula, but you do see the individual stars in there. And one thing they discovered was that one of these stars in there actually tends to flash on and off. And so that is the pulsar. So that there is the pulsar left behind. Now, we tend to get lucky here because if it had been rotating like perpendicular to the line of sight, we never would see it flashing on and off. So we just happen to be fortunate that we do see that, and we actually see evidence of a pulsar. Pulsars, neutron stars, pulsars are basically the observational evidence of neutron stars. And they're essentially like a giant nucleus. 1 cubic centimeter, that's like about a sugar cube or a thimbleful size, would weigh about 100 million tons. This is unbelievably concentrated. Magnetic fields, vastly stronger than the magnetic field of a white dwarf. White dwarf magnetic field is much stronger than a sunspot magnetic field, and a sunspot's magnetic field is vastly stronger in some cases than the biggest magnetic field on Earth. So neutron stars have incredibly huge magnetic fields, way bigger than we can ever produce in a laboratory on Earth. So our study of what happens in this level of magnetic field largely comes from theoretical analysis. They rotate very fast because of conservation of momentum. The charged particles, the energy produces positrons and electrons. They slam into the poles, and that produces the beam of radiation that comes out. The neutron star itself has probably a solid crust that's pretty thin, a mile or so thick, and then maybe about 10 miles across on the inside. Okay, the crust is actually individual nuclei and maybe even a couple of a few atoms stuck on there, and the inside is primarily neutrons. There's a few other particles in there. There's a few muons and mesons and protons, electrons, and things in there, but it's mostly neutrons on the inside. Not just neutrons. It turns out that the neutrons are what we call superfluid neutrons. Now, superfluid is a very interesting thing, and that is that at subatomic or condensed matter regimes, you have quantum mechanics plays a role, and what will happen is neighboring particles will interact with each other to act like a single particle, and then they can have particles come and go out of that single particle and still be a single particle, even though it's not the same particles in them. This makes superfluids have special properties. One property superfluids have is no viscosity. So imagine you have a bucket. If you have a bucket full of water, if you have a tiny leak in the bucket, then water is going to drip out. Well, imagine then if you had a bucket that had no bottom. So you just put water in, just go straight out. Instead of leaking out, it just drops straight out. Well, for a superfluid, if you have a bottom here but a tiny little hole, it's as if you have no bottom, and it'll just like go straight out. So superfluid just runs as if there's no viscosity at all. The other thing is the superfluid, in a sense, experiences space outside of its container. So the superfluid is not just in that spot. The superfluid is simultaneously experiencing space around here. So if you were to pour a bunch of water onto the tabletop, it would run off because it's heading towards lowest gravity, lowest potential energy, gravitational potential energy. A superfluid in a container will actually climb up a container and run out because it's still reaching the lowest level of energy because it's experiencing less energy on the outside. So superfluids behave really weird. The other thing about superfluids is they don't rotate. They have no angular momentum. Well, conservation momentum is very important in physics. And so what happens is if you have a rotating substance and you cool it. Now on Earth, the only substance we can make superfluid is helium, liquid helium cooled below about 2 Kelvin. And so you cool it below 2 Kelvin or 2.2 Kelvin and it'll suddenly turn into a superfluid. But if it's rotating beforehand, you have to conserve angular momentum, and so you conserve angular momentum by having little columns of just ordinary atoms sitting there spinning. And so that gives you your angular momentum. Well, as you slow down the rate of spin, then you don't need all these columns, and so one of them will just disappear. It'll evaporate. And so that means all the others have to speed up to take the angular momentum from that. Well, if you were looking at the light curve of a pulsar, and this is what we call the Vela pulsar, the constellation Vela, as time passes, what happens is it's slowing down. Now, why would it be slowing down? It would be slowing down because the neutron star, the pulsar, is grabbing all these charged particles that are around it, slinging it around in its gravitation and its magnetic field. These particles spinning around a magnetic field give off energy. The energy has to come from somewhere. It comes from the pulsar, so it slows down a little bit. As it slows down, at some point, one of those columns of normal things, the superfluid goes away, and the entire neutron star adjusts the spin rate. It speeds up a little bit, so the period drops really quickly. The technical term for this, and yeah, I know it doesn't look technical, but the technical term that astronomers use for this variation in the light curve is a glitch. Okay, so remember, a glitch. I often actually ask that on test questions, see who was actually paying attention. Okay, so a glitch is this change in the rotational rate of the light curve here in a neutron star. Okay, all right, so when you get the supernova, the neutron star can do weird things. Sometimes when a star blows up, it blows up asymmetrically, and so the expanding cloud of gas goes out, and the neutron star goes spewing out at an angle. So there are a couple of neutron stars that are actually moving at high velocity through the galaxy, separate from where the supernova originally went off. And so that makes it kind of interesting because it is possible that there are these small, unseen, high mass objects flying around the galaxy at high velocity, separate from where a supernova was in the ancient past. And so if you're one that really worries about the end of the world, that's actually something to worry about. Something about the size of the sun, or more than the size of the sun. Remember, the original core of a star had to be above 1.4 solar masses to collapse. So supernovae of big stars can leave a neutron star bigger than the Chandrasekhar limit. Now, it doesn't have to be bigger than the Chandrasekhar limit. What happens is that the original core had to be bigger than 1.4 solar masses. The neutron star itself could be a little bit smaller. It could be 1 solar mass. But they could be bigger than that. But even so, something the mass of the sun getting anywhere near the solar system, whether we see it or not, would drastically alter the orbits of the planets.